So, David?
All right, thanks, Marty. Good to see everybody. Welcome to the first seminar for the semester. Just one note of activity in the department before we get started with Drew's presentation is that we do have our share and learn today. I sent out an email. We'll do that immediately following the seminar from 1 to 2, so you can join us on Zoom. If you want to share anything new that you've learned on your digital learning experience, or you have a question for us, we can tackle that as well. All right, so it's my pleasure today to introduce to you Dr. Drew Schiavone. He is an extension specialist with the University of Maryland. He's based in Keedysville at the Western Maryland Research and Education Center. Dr. Schiavone specializes in heat and mass transfer with an agricultural framework. His primary research interests are in post-harvest storage, technology, and instrumentation to reduce quality losses during harvest, handling, and storage. Secondly, he conducts research on the efficiency, production, and use of energy on farms so they can maintain cost-effective and energy-efficient operations. As part of his extension efforts, he works with the diverse audiences throughout the state to help them make informed decisions about energy conservation and clean energy technology. Dr. Schiavone received his BS and MS from the University of Florida's Agricultural and Biological Engineering Department, so he's a fellow Gator, and his PhD in Biosystems and Agriculture Engineering from the University of Kentucky. Prior to coming to UMD, he led the Sustainable Agricultural Program at Andrew College in Cuthbert, Georgia. So let's please welcome Dr. Drew Schiavone to our first fall ENST seminar. Drew, it's all yours.
All right. Well, thank you, Dave. Thank you for the introduction, and I'm glad to be a part of this first seminar for the season, for the semester. I recognize a lot of faces that are on the line right now, and look forward to meeting and having discussions with the rest of you as time permits. I know it's not ideal having a conversation like this virtually, but nevertheless, I'm glad to be here with you. So I'm gonna attempt to share my screen. We can get started on presentation this morning. Let me know if any issues arise with that.
We're good.
All right, fantastic. So before I dive into that, I'll just kind of, connect a little bit of dots there with the introduction that Dave provided. My background as an agricultural engineer, a lot of the extension efforts that I'm involved with through the University of Maryland and applied research as part of that, a lot of it's geared towards the agricultural industry and sector. And I'll just, add to that. That's not all of the extension work that we do in the energy sector. We do a lot with residential, commercial, small business, and industrial energy issues. I don't want to spend too much time, discussing that, though. I want to make sure I have time to get into the topic for today, but I will, before we wrap up the discussion today on biofuels, I'll show you, point you to our website, our energy extension website on the UMD extension page, where you can find more information about the biofuel production we're talking about today. You'll find a host of other information on solar, on farm energy, home energy, and other topics there as well. So I'll just try to make a note to come back to that before we wrap up today. But with that said, I'll go ahead and jump into the topic today, and it has to do, I know it's kind of a convoluted title there, but I'll just simplify in sharing with you that it's essentially taking agricultural materials and producing biofuels and biochemicals. And so we'll talk about some of the different pathways that takes. This is an area of research that I've been involved in for a number of years, going back to my days as a doctorate student at the University of Kentucky. It's an area of biofuel production I'm still engaged in now, albeit not so much from a field research standpoint, but I do a lot of work from the computer modeling and simulation sitting behind a desk. So I won't bore you with, you may worry that I'll bore you with some of the mathematical details of modeling. I'll highlight some of those, but really I want to show you the framework of how such a system that we're proposing would take place. And so I'll point out some of the other partners that are involved in this. My alma mater there, University of Kentucky, a number of other research institutes over the years, including USDA and some private partners, Case New Holland, working with the machinery, mechanization, and agronomic production side of things. But I'll start just by giving a broad overview of the concept for the production of this biofuel on farm. And you'll see kind of the objectives there in the top. It's primarily to develop an on-farm high solids biomass conversion system. And that's kind of a mouthful, and it encapsulates a lot of content within that. But the idea, again, is to utilize the space and time that's available on a farm to produce biofuels, as opposed to bringing that raw material to a centralized processing facility, a biorefinery. There's a couple reasons that we're proposing to do this on farm, and for one, from an economic standpoint, you don't necessarily see a benefit from transporting bulk materials. We're talking about a lot of bulk materials to a central facility that will eat up transportation and other factors there, eat up your fuel cost. You don't want to use more fuel producing the fuel than you're generating. So that's one aspect, that we're proposing to do it on farm. It may not be 100% as efficient as a centralized commercial facility would be in producing biofuels, but there are some tremendous benefits that we'll get into moving forward in this discussion. It's a high solids environment. We're looking to minimize the costs to the system as much as possible to make it not only financially sustainable, but also environmentally sustainable as we produce biofuels. So let me just jump in by kind of running through some of what this process involves. And this is all from a research and development standpoint. We're not at a application, a real life application at this point in time, but you'll start to see some of the feasibility of this system as we go forward. So the idea is to take agricultural materials, starting with agronomic production. A number of those partners I mentioned earlier are involved in that side. I'm not going to be able to discuss in too much detail. It's just not my expertise talking about crop production. But I'll mention some of the different crops that we're looking at, everything from the agricultural residues, that would be things like corn stover and wheat straw, things that are left over from a grain harvest. And so we're not proposing necessarily that a farmer transitions to a new crop production system, but this adds an additional revenue stream to their operation, where they may be harvesting corn in their combine. That leftover material can be converted into biofuels, and we're primarily talking about biobutanol as an alternative to ethanol, has a really good energy content. Talk about ethanol, acetone, other organic acids that we can produce from this. But those are some of the ag residues that are readily available on a farm. And rather than transport some of these materials, as I mentioned, to a central facility, there's benefit in converting them right there on the farm. Where you might, in the illustration, if you can tell from that illustration, it may take 4 trucks loaded with material, whereas if you produce your dilute stream of biofuels, you would only need 1 tanker truck to replace those 4 vehicles. So there's some trade-off there in terms of getting a concentrated product to ship to a refinery. The other side is looking at energy crops, dedicated energy crops, things like switchgrass and miscanthus, and I'll spend a little particular attention to these in our discussion today. These are warm season perennial grasses, very high yields, very good production. These are very large grasses, if you're not familiar with them, that grow 8, 9, 10 feet tall or more. But we can produce these on land that's not actively in use by grain production. It won't compete with corn production and conversion to ethanol. So we're looking at different land systems that could operate within. Regardless of the feedstock, the idea is to densify them into bales. It's a very cheap format to produce. We're not grinding it up because, again, that takes additional capital for the equipment to grind it and the energy to run those systems. So we're proposing a high solids environment where we densify the material by baling it. Agricultural materials have very low energy content. If you compare it to a conventional fuel like diesel or coal, the energy content is rather low. So we're increasing the density of these to run a solid substrate conversion on it. It could be, I'll share some of the specifics of that later, I guess, but the idea is to get that material very dense. There's some benefits from the fermentation standpoint we'll talk about. But the idea is then to load it into a bunker silo, a modified bunker silo. We're looking at infrastructure that are already available on many farms, especially dairy farms and other environments, where you can store the material at the convenience of the farmer when they have time, and they're able to go in and process, then they can go in there. It's in a protected environment in the bunker silo. And then we can just use that same silo as a reaction vessel. Now in the illustration, you'll see overhead irrigation and sprinkler systems. That's for the purpose of inoculating this high solids environment. We'll talk about the specifics of that as well. Flushing the end products out. You don't want to leave your end products suspended in that high solids environment. It'll inhibit further reaction from occurring. And also it's just a way to remove the end products, and you'll collect the leachate, the runoff at the bottom. And then, pre-treatment runs with a couple different pathways. It could be a fungal system. One of the promising systems we're talking about is with white rot fungus, which is a naturally occurring fungus in woodland environments. It breaks down woody materials. The other option is delignification with a Fenton reaction, and that uses hydrogen peroxide and an iron solution to break it down. Different pathways, but the same idea is to break that lignin down, get access to the fibers, and then running your conversion and fermentation with a series of bacteria. As I said, the system in that bunker silo, it flushes the end products out. What you're going to get when you collect that fluid at the bottom is a dilute stream of water, butanol, ethanol, acetone, and other acids. And so it's really not feasible to refine that on the farm for economic standpoints. It's already, we're proposing a bit of management in addition to the operations that a farmer already undertakes. This is as simple as would be feasible, but we don't want to add just astronomical economics to the picture and refining it there. So once you get to your dilute stream, you can concentrate it down. You don't want to ship all that water weight. It'll require additional vehicles to transport that to a refinery. So the idea is to use something like charcoal absorption. That's something that's commonly used in groundwater remediation for petro spills, things like that. So that's one option. But again, the overall idea is to run it up to that point on the farm, which works out from an economic standpoint, and then transport that to a refinery for further processing. You can blend it with fuel. So, that's kind of a broad overview. What I'll do is I'll kind of show you the overall scope here of the aspects that all have to fit together for this proposed project to work. Starting with feedstock development, that highlighted region. Of course, it has to do with, this all depends on how good of a yield we can achieve from an agronomic standpoint. So I'll spend a little time, I'll dive into a couple issues there. I'll hover over others from kind of a broad perspective, and then we'll transition to more of the product development side of things. But just to get started on this, and again, this isn't my expertise in the crop production side, but just from a general sense, you want to select varieties of grain and agricultural commodities that have high yield and high sugar content. The same thing with your dedicated feedstocks like switchgrass. You want good cellulose, you want good digestibility, you want to be able to convert those products very well. And we're looking at different soils and different land use scenarios, and there's a large aspect coming in at that point. What I can comment more on is the harvesting and collecting side and looking at it from an energy efficiency standpoint. When you're running your equipment over the field, even starting at that harvesting stage, you're consuming fuel to run a tractor or a combine or something like that. And so we need to make this whole process from feedstock production through the product production, we need to make it energy efficient. And so there's a couple, basic aspects that many farmers overlook, and it's part of our common extension education programs is keeping your tires inflated on your equipment for better fuel efficiency, using single pass harvesting systems. And what I mean by that is getting all of the harvesting jobs done in one single pass on your field. So you don't want to drive your tractor over the field and collect the grain one time, go back over it a second time and mow the remaining material, and the third time collecting and baling the material. You want to achieve all that in one single pass. You'll see in the photograph there at the bottom of the slide an idea of running a mower in the front of your tractor and a baler in the back. And so you're only having to travel over that field one time, improving the overall fuel efficiency of this operation. Because again, you don't want to waste fuel while you're producing biofuel. We also want to do things like increase the bale density. As I mentioned earlier, the energy content is rather low in this feedstock. And so in order to transport this material more efficiently, if we densify the material, we can load more of it onto a vehicle. Oftentimes, whether you're talking about a trucking operation and you're loading the raw feedstock onto a truck, you're going to run out of volume on the truck. And so if you squeeze that material down to a tighter compact form, the tighter you get it up to a certain level, you're going to be able to transport that a lot easier with a lot less trips back and forth. You don't want to invest in high capital costs to condense the bales beyond reason. Again, you're eating into your revenue by doing that. But we're looking at very low-cost systems where we get high-density bales. And you can only go up to a certain threshold with conventional baling equipment, and we'll talk about that in a little detail later. But one technology that we've worked on is using crushers as the material is pulled into the baler to crush the nodes. Simple, if you think of rolling pins, essentially, to crush the material and squeeze it down so you get a tighter compaction. And so all of these kind of pieces have to be fit within, as I've noted in the presentation, fit within different modeling frameworks from life cycle assessment and GIS information to evaluate what works and what doesn't. And we'll talk about some of the economics to this that have been developed through the modeling. If we have time, we'll get to that. But the idea is again, producing these crops very efficiently and collecting and harvesting them. So I'll continue to kind of go back to some of those points, but just now to give you a scope of the product side. So after the material is harvested, that's when it goes into a storage facility on the farm. And again, we're proposing the use of facilities that are already available on many farms, including the bunker silo that you see in one of those photographs I've shared. This again, in the photograph, does not have the irrigation system installed, and it's not covered. We're proposing an anaerobic digestion. It would be covered and have the irrigation to percolate water. But this gives you an idea of what we're discussing is the material can be loaded in there, stored for some period of time, and a farmer can then operate that system and start pre-treatment when he has the time available. And so that's another advantage to running this on a farm setting. So pre-treatment, I mentioned some of the different mechanisms that can happen. We can inoculate that and feed the bacteria and the pre-treatment in through the irrigation system. There are other alternatives to that, but that's one framework that we're working within. That may take some time, days or weeks, and then running the fermentation, which is the bulk of what's proposed here. And in this particular in this particular pathway, we're talking about a co-culture of two bacteria. One is the C. thermocellum, and this is an anaerobic environment, so there's no oxygen, and it's requiring a high heat. And so there are some ways that we'll need to supply that heat. One is to use the leftover material. Whatever material is not degraded, we can use that to gasify and supply heat through a CHP system. It may be somewhere between 50 and 65 degrees Celsius. So we're talking about a controlled environment that we have to achieve for that bacteria culture to work. But breaking those sugars down into the fuels we're talking about, principally biobutanol as an alternative to ethanol, and we'll get a host of other products mixed in that dilute stream that we collect. But through flushing of water, we're removing the end products again, collecting those end products in drainage strips beneath our reactor. Again, that's a dilute stream, so it has to be concentrated. Another benefit to concentrating, not only are you cutting down on how many tanker trucks you'll need to transport it, but you can reuse that water and use it for the next fermentation cycle that you proceed with. And this fermentation process, this might be repeated multiple times with the same substrate, and you might repeat it 8 or 9 times. It really just depends on how well that lignin is breaking down and how that reaction is proceeding. So it can be repeated multiple times. That water can be reused. Again, you'll be left with some material because we're not going to be able to convert 100% of it. It could be used to supply heat by burning it, or we could land apply it. It's quite a bit of organic matter, possibly phosphorus and potassium and nitrogen in it as well. So it could be land applied with a manure spreader. There's some aspect to that as well. Again, that's kind of the broad overview of this whole research endeavor. I'll talk about some of the specific engineering analysis that has to go into this. And this has been an area that I've been especially involved in for many years. But to assess how much water we're going to need, how we're going to percolate the water, what are the flow rates we'd expect, how the temperature is going to transfer through the material. We need to maintain all of these conditions within the reactor, and that's a lot about what I'll share with the rest of our time today is how we quantify and evaluate some of these parameters for these essentially living ecosystems within the bale. And so what I've shared is 2 feedstocks that I'll spend most of my time discussing, just so you can kind of compare and contrast. I don't know if you'll be able to tell from the slide that I've prepared here, but the feedstock on the left, the switchgrass, it's a very, in some ways, very similar to miscanthus, but the switchgrass is much smaller stem diameter. You get a much tighter compaction and not as much pore space as you do the miscanthus. So you may be able to tell on that miscanthus that the stems are larger and you get a lot more air pockets. And so just looking at the 2 feedstocks, there's quite a bit of variability depending on what material you're using for this reaction. You may have higher oxygen counts in one material than the other, which would be the difference between aerobic and anaerobic reactions. You'll have different temperature transfer, different rates of fluid flow. All that has been important for us to evaluate from the start of this project and moving forward as we do more predictive modeling and evaluation to run this operation. We've looked at a range of densities from the lower, more conventional density levels of 8 pounds per cubic foot up to about 16. Any denser than that, again, that would require additional equipment and expenses associated with it. And you would also get quite a bit of high solids content that would inhibit some of the reactions from moving forward. There's a number of reasons that we're looking within that density range. To assess the fluid analysis, one of the things we need to know, as I mentioned, is how much water would it require to fully flush this material, and we really had no idea going into this. You'll see just how porous this material is. It's very low density. That bale is not sinking very well. It's like a log floating there. And so there's some challenge in of course, we're not submerging the bales like that. We're percolating water from above, but this is one assessment that we're able to conduct to determine how much water we're going to need for this operation. You'll see, depending on the density and feedstock, it's anywhere from around 60 to 75% moisture content when it's fully saturated. So it's quite a bit of water. Both of those feedstocks, switchgrass and miscanthus, there's some difference there. The other materials I mentioned earlier, like wheat straw, they're similar in a lot of ways and they kind of fall within that range, but that's kind of I share these feedstocks because they're kind of the lower and upper bounds respectively. You'll also see some density dependence. Again, as those bales are formed tighter, you get more restriction of the porosity and you're not going to have as much room for air to enter. And that could be a mixture of air, vapor, or other things, but you're not going to have as much gas volume surrounding the material. So that's going to impact the way this reaction occurs. Now, as the material drains, once it's wetted, it starts to lose some of that moisture. And I just want to point out how quickly this material drains initially. If you look at, in these figures for both materials, within the first, 5 to 10 minutes, you lose, upwards of 20% of that moisture that it was saturated with. So they do lose moisture rapidly, very quickly. So if you are flushing to that point of saturation, which may or may not be feasible or practical. If you saturate it to that point, though, you lose a lot of that liquid. And for the most part, for this data shown, maybe a couple days worth, it's sitting pretty consistently around 55 to 60% moisture content. So it remains fairly wet. And that's water is really, that free water is really taking up any pore space. So for the most part, when this material is wet, you're going to have anaerobic conditions occurring. It's only when you drop down below 40 or 30% moisture content where you're actually going to have more aerobic reactions occurring. We've looked at the flow rates through many of these materials. This is a system we devised to evaluate the flow rate at a lab scale. The idea is adopted from environmental engineering and soil science studies. It's evaluating a term known as hydraulic conductivity based on Darcy's law, but we're basically supplying water. You'll see that pale yellowish tank. That's the water supply. The wooden and metal contraption that you'll see in the front of that photograph, that is the system that encapsulates the actual baled material. And so we're able through this system to set a constant head level of water above the material, and that water slowly drains through the material as we're proposing with percolating water through the system. Now in this case, it's fully saturated. This is again the upper bounds of the amount of water that we would need in a real application, but it gives us some framework to move forward with. So we're quantifying this nominal flow rate known as the hydraulic conductivity through that water. You'll see some values that we've added to the literature on this. Again, what you'll see is the flow rate is density dependent. Again, the more tightly compact those bales are at high densities, the more restricted your flow rate becomes. And so, we propose working anywhere in that range. Now this is in kilograms per meter. I shared with you earlier feet per pound per cubic foot, but same idea is looking in this range of densities. And we're going to get different outcomes based on the different densities. And all this has to be kind of going into our life cycle assessment to see what's economical and what's feasible as an overall endeavor. But we've developed models based on that, and I'll share some of the work we're doing with that now, currently with some of these modeling systems. As I mentioned, we probably will not fully saturate the material that require tremendous amounts of fluid. So we've done quite a bit of assessment when the material is unsaturated. The flow rate's a little bit different when the material is drier. So we've used, again, various mechanisms of looking at moisture and fluid flow. We've done some inverse modeling using Van Ganukten's method. and infiltrometers, basically controlling the pressure, the tension, and how water flows through different pore sizes within the material. All that to say, we've again added some literature to this and values to the literature here. We can look at what's commonly reported for sandy materials and how water flows through sand and gravel. And I've kind of indicated there that we're in this range. All the biomass that we've looked at has been within this range, kind of equivalent with the flow rates of water through sand. So using this information, we can kind of assess how feasible it is to flow, and it is rather, but it does require some water depending on how wet you need to get it with the inoculation and flushing. So that's a bit that's happening on the fluid side. Looking at the temperature and thermal assessment is important as well. As I mentioned, we have to control the temperature of the reactor to get optimal efficiency for the bioconversion. But also just from a storage and management standpoint, it does having wet material poses a safety factor that you have to account for. If the temperature gets too hot in the material, the material can spontaneously combust or even start to degrade before the reaction occurs. And this happens quite often in just traditional farm storage operations. We've breaking open a number of bales, just working on farms and seeing the degradation that you'll get just from microbial activity within the bale, even to the point where it will get ashy or burn, and in a bad scenario, as I mentioned, it could combust and burn up if the oxygen's there. So some of those factors are important to us in understanding the temperature and how it moves through the material. So we've employed a number of instrumentation and modeling systems to look at this. What you'll see here is a prototype sensor that we have used to evaluate some of these temperature properties, things like thermal conductivity, diffusivity, specific heat. It's based on the line heat source method, where we supply a constant voltage into the material through one probe, and we measure the temperature change, and we can measure the temperature on the secondary probe to evaluate some of the other parameters. And I won't get too much into details unless there's questions on that later, but this is the prototype instrument. Again, you'll see the size of this. It's very difficult to fabricate. It's not a real practical tool in real life. It's more of a research and development tool to quantify some of these thermal properties, but we've used that in various settings throughout this project to evaluate how the temperature moves. This is kind of a fun picture, at least from my standpoint. When we hired a HVAC contractor to spray these bales, there was a lot of scratching the heads and wondering what we were doing. We eventually invested in our own spray foam equipment, but the idea here was to coat certain surfaces of these bales, and now we're talking more of the sizes that we're proposing in this system, closer to 3 by 4 by 8 feet, getting quite a bit larger here, but coating the surfaces of that bale to control which way the heat moves. So in some cases, the heat's moving up and down, left and right, forward and back, and different combinations of that. So we're able to assess how heat moves in different directions, and that's important for us to know, because this is a very different material directionally speaking. If you're not familiar with how a bale is created on the farm, basically the baler pulls in a piece of material or multiple pieces of material, and there's a plunger that pushes that onto the previous layer. So you can maybe helpful to think of stacks of paper on your desk. You'll just keep stacking those sheets of paper. Now what we found, and I'll share some of the broad results of this, is if you're looking at the top sheet of paper on your desk, heat transfer within that sheet, within the top sheet, it's pretty much the same from top to bottom as it is from left to right. The only difference we're seeing in how heat moves is down when you penetrate through the stack of paper, through the longitudinal axis of the bale. And we're having a lot of different physical scales that we have to account for, discontinuous pore channels where vapor can't move and other factors come in. So there's some unique aspects that we'll mention. And I know I'm kind of getting low on time, so I'll just share some of the basic results here. In the figure that I shared on the bottom of the slide, you'll see one of those lines, the dotted line, is just off the charts. It doesn't fit within this scale. And that has to do with what I just shared with you about that longitudinal axis. There's very different heat mechanisms, heat transfer mechanisms occurring in that direction. So it requires some, unique consideration in that perspective, different than some of the mechanisms at play within our bulk material, and I'll come back to that. Some of the early work that we have done with this information is basing some computer simulations on conduction. And so we're just considering the bale to be a simple solid material. In reality, we understand it's not, but this was a starting point for some of our early computer modeling. And I won't bore you with the details of too much of this, but just basing it on a simple conduction model, running simulations on that, with one of our primary goals was to do kind of a sensitivity analysis on the parameters that we quantified. So if you look at the sensitivity here, alpha would be one of those thermal parameters, the diffusivity. If we just change that value by 10%, plus or minus 10%, we're getting a significant change in how our model predicts the real heat generation that's occurring in the material. And so that becomes an issue that's really important to have that quantified for each feedstock and have an adequate assessment of it in different directions. But you'll see in different scenarios, heat generation will spike at some point when the microbial activity is the highest. If you start to dry that material, that microbial activity generally dies off in the drier environments, and you'll get lower heat generation. I'll kind of skip some of this information and touch on some of the highlights here. As I mentioned, I know I'm low on time, but where we're moving with this now, and some of the work I'm involved in now, is working on more porous modeling systems, so we can predict different safety factors that I mentioned in terms of temperature and fluid control in that reactor. And so this is a very innovative approach that we're not only looking at this whole solid material, but now we're looking at a much smaller scale as well, looking at individual stems of the material. And so understanding some of the physical realities that material has, as well as the interaction that material has with the air pockets that surround it. And I say air pockets, but that could be any gas or fluid, liquid in the environment, depending on what stage of the operation you're operating within. So some of the details for the outer domain, again, I won't touch on too much of this, but we're looking at natural convection and buoyancy effects as hot air rises through the material. It carries vapor with it and other aspects. I may point out a couple facets when we're looking at the inner domain, or what I mean by that is the individual stems. So we're looking at a very small scale. We're having to account for these very minute phenomena that occur on individual stems, even looking at how the mass or vapor transfer occurs between the stem itself and the surrounding air or liquid. There's waxy coatings on the material that inhibit some of the mass transfer, and so under different scenarios, that wax coating may be more or less broken down, and that has to be accounted for. But there's a lot of heat and fluid reactions happening on that scale that we're accounting for. We're incorporating drying models in there, and one other aspect I'll point out, we have the framework now incorporating aerobic respiration, so when there's oxygen there. As I mentioned, what we're proposing with the bioconversion process is an anaerobic reaction, and we're not quite there from a modeling standpoint yet. It's a work in progress. The aerobic respirations, this part of the framework's fairly straightforward. It's easy. It's not super robust, but you'll see it's based on just the stoichiometry of the reaction. If you're converting the sugar into carbon dioxide and water, we've measured and have the carbon dioxide output measured. So from that, based on the stoichiometry, we know how much heat to expect, And that's where our microbial model is at this point. Again, not truly robust, but it is very important to have that in there because there is quite a bit of microbial activity happening. Now, all these pieces come together, a lot of information I'm sharing with you, but all these different mechanisms have to fit together on a small scale and a larger scale, and at the reactor scale. The original first version of this model, it was taking upwards of over a week for the computer simulation to run. Significant improvements in that, and we're continuing to build off the framework. We've used it to evaluate microbial activity in different field experiments. In particular, you'll see we've looked at maximum temperatures. Again, you want to make sure you don't reach unsafe temperatures, so that's one way to predict this before you get into a compromising situation. We're able to see the profile. You know, looking at the side of a bale, we can see specific regions within the material that might pose problems. We'll see if we're achieving the right temperature in the right place, and if it's too wet for some microbes to effectively convert that into product. As I mentioned, you know, we have some limitations to the model. We're still developing it. What we see is that the lower moisture, see on the bottom of our of this slide, you'll see we're getting pretty good accuracy with the low moisture. 10% and 20% moisture is fairly accurate. It's when you start to get higher, and that's, again, when you hit 30 or 40% especially, you're switching from aerobic to anaerobic. And that's where our model starts to break down right now. And so we have to account for some of that and some of the liquid diffusion as well that's occurring within the material. So it's a work in progress there. One final thing I'll kind of leave off on is looking at the dry matter losses and being able to predict in a bioconversion setting. That's exactly what you want is for that dry matter to be lost and converted into product. But in storage operation, it's not favorable because you're losing the product before you start. But our model simulation, again, fairly well prediction up until a point. You'll see at the moisture 40 level, that's really not a real life prediction there. It's 143% dry matter loss, which obviously you can't have more than 100% loss in material. So that's not realistic. But again, it indicates some of the work that needs to be progressed in this area to account for some of the anaerobic activity that's happening there. But nevertheless, that gives us some idea of where we stand. With that said, you know, again, thank partners that have been part of this broader research project. And as I mentioned, I'll kind of indicate where you can get some more information on all energy things in Maryland, not just bioconversion and biofuels, but there's a number of other topics relating to energy efficiency in the home. You'll see sections for farm energy and solar energy. You can sign up for the energy newsletter that we put out with Extension, Energy Extension, to find out about news in the state. You can connect with us on Twitter and Facebook. And one thing in particular I'll point out is our ongoing series starts at the end of this month on-farm solar training and covering a host of topics from seeing a broad overview of the solar sector in Maryland, looking at the specifics of installation and maintenance and battery storage. And this information is relevant not only to farmers, but those of us in extension and research and other areas as well, from residential to commercial. So if you want more information on that, you can find that at the Energy Extension page. The address is given there. But I think I'm kind of over on time, so I will wrap up here and take any questions if there are any.
Great. Well, thank you very much, Drew. That was a really interesting presentation. And there are a number of questions that have been emerging here. So let me see if I can pose these. You might be able to see them yourself in the chat box if I don't articulate them quite as clearly as they're written here. But so here, one question is there a minimum crop acreage that's necessary in order for this sort of to get this to run effectively on a farm, or is that still sort of a research goal, trying to figure out that kind of a answer?
That's a very good question, and it is very much a research question, and it depends on some of the economic some of the economics over the next 5 to 10 years, depending on price of feedstocks and what you can get for the bales, what you could get for some of the fuels. So no, not really an acreage, but that's going into the work that the University of Wisconsin has really headed up on the life cycle assessment side. And one of the biggest things is in setting an incentive level to make this profitable for farmers. So really, there's a lot of factors. It would depend, as I said, on the pricing in the next 5 to 10 years. If you're getting $40 per ton of feedstock, or if you're getting 50 cents per liter of biobutanol, it really depends on that. It also depends on the feedstock and what kind of reaction you're running. The one I talked in particular about, I spent time talking about white rock fungus and things like that. But if you're running that reaction, will have a very different pathway than maybe what you would see with a Fenton reaction or other bacteria culture. So all that is to say, yes, it is a kind of a research standpoint that I couldn't sit here today and give you an acreage on that. But
right.
That would be where the research is headed, is giving some logistics for the economic side for farmers to base a decision on.
Great. Thank you. Someone's wondering whether there's been any attempt looking at hemp as a potential feedstock for energy and organic chemical production.
Yeah, I think absolutely, and not a part of this research endeavor in particular. I haven't kept up on that hemp production as much, but I mean, there's a lot of groups out there looking for, valuable products to come out of that. I think there is some research. I don't know where it stands right now. I've just seen it in passing in the news, but I don't know if, honestly, I don't know if there's an industry for it, just because I'm not familiar with it.
Right.
But I know there's at least the hemp industry will tell you there's a lot of practical products to come out of it, and biofuel may be one of them. I'm not sure though.
Okay. Dr. Wiles asking, he says, I'm concerned about the unintended consequences for soil health and ecosystem services, including climate change mitigation. So the main issue is the impact of removing crops in the above ground residue that normally would be returned to the soil, which would then increase soil carbon sequestration, or at least to sort of reduce the decline in soil organic matter during cropping systems. So, maintaining or increasing soil organic matter is, a critical part of sustaining sustainability and productivity in soils, and also it serves as this major sink for removing carbon from the atmosphere. So, and maybe other aspects of soil health too. So how would you respond to that sort of a criticism where instead of putting that carbon back into the soil, your goal is to kind of convert it into biofuels?
Yeah, that is a very fair question. And I won't say that this operation works 100% of the time in long-term sustainability. That's part of the research aspect of it. And, I continue mentioning that life cycle assessment and being a key piece of the puzzle here, not just from economic standpoint, but exactly in line with what you're mentioning in environmental sustainability. You have to, in this life cycle assessment, you have to weigh some of the costs and benefits, and I won't be able to provide specific numbers or anything today, but you have to weigh the costs and benefits of replacing traditional fuels with biofuels, and whether or not we're going fully electric vehicles in the future or not. I mean, that's a broader picture to account for. But certainly we want to account for the fact of replacing traditional fossil fuel with biofuels. From the land management standpoint, yes, you have to make sure that you are, implementing proper land management. And I very much agree with that sentiment that you want to protect the ground, which is why one of the advantages, you're not breaking the material down as much as a centralized facility would be able to do. A commercial facility will be able to remove and break all that lignin down we still have quite a bit of organic matter that we're kind of investigating in terms of reapplying that to the soil. And a lot of what you're talking about, it could be chopped up or spread, because we have quite a bit of lignin left over. So that's the attempt, is to balance that, not to strip the earth bare. I don't think anyone would propose, investing completely in biofuel at the expense of land. So that's very much a aspect of that. As I said, I can't provide numbers or anything in terms of, land and sustainability in that standpoint, but hopefully that gives kind of
okay.
That's a generic answer, but that's very much a piece of the puzzle.
Okay, good. Here's another question. It says, I have a question going back to the dewatering and charcoal. The economics of the cost of charcoal and disposal costs and life cycle costs of charcoal production seem like they would be high. Has work been done in assessing these dewatering costs? He says, I know in anaerobic digestion that dewatering has been deemed, it's a cost and very energy intensive process.
Sure, I don't know too specifically about the charcoal being used. There are some other filters we've looked at. I'm not sure what they are off the top of my head, but I would imagine that would have some impact on that industry and production of charcoal for that. I couldn't provide much more information, but if anyone wants to connect with me on that issue, I can share some of the other filter technologies that have been part of the research and development stage as well. But that's best I could do at this point.
Okay. Yeah, that question came from Dr. Lansing, who does a lot of work with anaerobic digesters. And then here's a question. Someone was asking, is there enough miscanthus available in the country to kind of support this project, you think?
Yeah, I don't know what the production is right now. This would be, part of this would be market development and getting there. Same projections in 5 and 10 years where this would drive. I think there is tremendous area for growth acreage wise in that, especially on marginal land that's not being used for crops. We don't want to replace traditional fuels, but divert corn production and other crops to food and other areas of the industry there. But if we're using marginal land and stuff, there's quite a bit of growth potential there. I'm hesitant to go much further than that, but I think no, we're probably not to support this industry, but we're not talking about a complete large scale operation. This is to add on a very small scale a business opportunity for farmers to invest in. So if they have a marketplace, even for their small acreage, that would be a revenue stream for them to sell an additional product. But no, I don't know specific acreage on miscanthus. Yeah. It would need to grow overall for the industry to be sustainable, and there be a marketplace for the fuel.
Okay. So there's a lot of working pieces in this at this point, obviously. A lot of questions you've raised, and you're working on some of those. Do you have any sense of where we are in terms of, how far off is it before this becomes something that you think might be viable for farmers to begin to implement? Is there going to be some of these systems set up on farms next year? Are we looking 3 years, 5 years down the road? Or how quickly do you think you're going to be able to answer enough of these questions for this to become something that's really is economically viable for farmers to jump onto?
Well, I think the next step will be pilot scale reactors and scaling up from there. So, I would say in the next several years, that would be where we'd want to aim with this, and partners are already having partners working on this operation. Farming operations, we'd be able to implement pilot scale production from a research standpoint, and depending on how things move forward, 10 years, we may have a working system that's viable and reliable. So it's kind of a tentative timeline, but yeah, going to pilot scale would be I think the next step in demonstrating feasibility on a large scale, because what we've talked about is more research and development at this point. So that's the next step.
Okay. A couple of comments have come in that I want to share. And Dr. Weil suggests that he doesn't really think there is that much, quote, marginal land out there, because a lot of the marginal land is suitable for no-till type agriculture. But Dr. Felton has said that he thinks that you could grow miscanthus or something on a lot of mined lands with very little additional inputs. So that may be areas that would be potentially suitable that wouldn't be competing for food type crops. Well, we're just at the witching hour. It's just 1 o'clock. And so I want to thank you, Drew, again for sharing a very interesting seminar on a topic that many of us are very interested in, and addressing these questions. And we wish you the very best of luck. And let's give a round of hand clapping, right, for Drew for his fine presentation. Thanks very much, Drew.
Well, thank you for having me.